Hey guys, hope all of us are doing fine. I'd like to welcome each and every one of us to my channel. And first, I'd like to appreciate our incoming members, and I would like to, of course, encourage them to feel welcome and engage us in the comment section. I also like to request us to kindly go to our description boxes of various videos that we have, of course, uploaded. There are specific links which are contained there, which, of course, have particular topics of interest, especially related to topics under the discussion. Now, in this case, I'm going to look at the inverse of a square matrix. And in this case, I'm going to use, of course, the first discussion we had discussed on the concept of using what we refer to as a classical adjoint. And of course, this is going to entail the use of the concept of cofactors and the minors that I've discussed in my previous video. Now, in this case, this specific strategy is going to, of course, assist us narrow down on the lengthy procedure that we normally use in finding matrices. And of course, it's going to be one of the ways in which we can easily obtain, of course, the inverses of a matrix, especially the square matrix. And in this case, of course, I'm going to elaborate on some of the relationships that we have, especially on the determinant and the inverses, and of course, the concept of a classical adjoint. Now, of course, I'm going to do that using a specific example of a matrix, which is a 3 by 3 matrix. So we're going to have a matrix A, which is given by different elements of 1, 0, 3 for the first row, and then we're going to have 2, 1, 4 for the second row, and then we're going to have 1, 2, 1, 2, 1 for the third row, given that specific order. So in this case, I've mentioned that we're going to use the concept of a determinant, and of course, our main aim is for us to find the inverse of this square matrix. Now, I've mentioned two ideas whereby we're going to find this one by the use of what we refer to as a classical adjoint. And I'll find this specific, of course, a classical adjoint as the transpose of the matrix of the cofactors. Now, in this case, this one, of course, implies then therefore that we're going to find the minus and the, of course, the cofactors of this specific matrix. And therefore, after them, therefore, we are going to find a relationship between this aspect of the inverse and of course the cofactors which I've mentioned. Sorry for that. Now then, in this case, of course, an inverse A can be defined or can have a relationship. I'm just going to mention that so that we, in our specific explanation, we're going to just elaborate on that. So an inverse A can be obtained by finding of course, this is going to be 1 over the determinant of that specific matrix, and this is going to be multiplied with the classical adjoint given as A. So this is A, which is a classical adjoint. So the product between 1 over the determinant is going to give us the classical adjoint of that. And as I've mentioned, the classical adjoint entails of course, the transpose of the matrix of the cofactors, and therefore we are going to find matrices of the cofactors by finding the minus of that specific, of course, a matrix, which is a 1, 2. So I'm just going to list the elements for the minus of that specific matrix, which is 1, 1, 1, 2. 1, 3, and then we're going to have M21, M22, M23. So this implies that these are the ith rows and the jth column I'm listing beside this minus, and then we're going to have this M3 to M3. 3. So in our previous discussions, we have discussed the concept of minus and cofactors. I'm going to put a link of that specific video in our description box so that it assists us to identify, or rather identify the procedure of finding this specific aspect of minus and cofactors. And I said basically that for us to find these minus and cofactors, we're going to have them minus given in terms of an n minus 1 by n minus 1. So which basically we're going to delete. For a square matrix, we're going to delete a row, a column, a row and a column. And therefore we're going to find the submatrix which is going to remain. For instance, if I have to delete the first column and the first row, So we're going to start with the row and then the column. We're going to remain with 1, 4, 2, 1. This is going to form a submatrix. So the determinant of this specific submatrix is going to form a set of of course, so I've deleted the first row and the first column, which implies that it's going to give me the determinant of this remaining submatrix for 1, 4, 2, 1 is going to give me, of course, what I refer to as a minor of column 1 and row 1. So this implies of course, the row and the column which I've deleted. And of course, we're going to see that basically for the first one, as I can give us an example, we're going to have this one given as the determinant of 1, 4, 2, 1, which is going to be basically 1 times 1, 1 minus 6. So 1 minus 6 is equivalent to minus 5. And that is going to give me a value for the minor of this specific, of course, first set, which I've given in that particular order. So in this case, sorry for that, this product is wrong. So this is 1 minus 8, basically. This 1, 1 times 1 is 1, 2 times 4 is 2 times 4 is 8. So 1 minus 8 is negative 7. So the value of negative 7 is going to be my first minor. And after we're going to have this specific range of values, of course, given for the specific minors and cofactors. So I'm going to fill up this specific array of numbers for us to obtain the respective minors. So from our board, we're going to find a range of numbers, of course, by finding the minors of this specific respect by deleting the ith row and the jth column. The remaining submatrix is going to give us a determinant which we have given in terms of the values of this respective, of course, minor. So we're going to obtain an array of numbers which are, of course, 6 in number. And of course, we had given the relationship between our, of course, minors and of course what we refer to as the cofactors. A is going to represent a cofactor, and we had said that in order for us to find a cofactor from this specific case, we had mentioned that basically a cofactor represents a number given as Aij, which is the product between the negative 1 raised to ith and plus jth, the summation of ith plus jth column, and that's going to be multiplied together with the minor of that respect ith and jth column. So this one implies that basically then therefore we're going to take the sum of the values of this specific ith and jth column in terms of numerical value. So for the first one, we're going to have negative 1, then raised to power 1 plus 1. So the sum of this is negative 1 raised to power 2. This is going to give us positive 1. So a multiplication between positive 1 and the value of the minor of this one, which is negative 7, is going to give us the value of the first cofactor, and that is going to be negative 7 in that specific case. So for the second one, we're going to have this specific ith and j of a row and column in that specific respect given in terms of, sorry for that. This is negative 1 raised to power 1 plus 2. This is going to be 3. So negative 1 raised to power 3 is going to give us a negative value, which is a negative 1. So negative 1 times the minor, which is negative 1 times 2, this is going to give us a value of a positive 2. So therefore, we're going to fill these specific cofactors in that particular respect until we find the final set of a number that, of course, is going to give us all the values of these respective cofactors. Now, this is going to be assisting us to find what we refer to as the matrix of the cofactors, and therefore I'm going to do away with this specific section since I've explained its implication, whereby we're going to see that therefore the matrix of the cofactors are going to be represented using, so we're going to have 7 as our first element for the column, the first column, 6, 3, and then we're going to have 2, negative 2, 2, and then we're going to have 3, negative 2, 1, negative 2, 1 to form specific elements for the matrix of the cofactors given in that specific order. So we have said that finding the matrix of these specific cofactors is going to play a vital role in that if we have a transpose over this specific matrix, then therefore we can call this one a classical adjoint. And of course, the multiplication between the 1 over the determinant of this specific, of course, matrix, then therefore it's going to give us the classical adjoint times the inverse of this is going to give us the inverse of the matrix. And this is one of the strategies that we're going to use in finding the inverse of matrices, especially for a 3 by 3 square matrix of this specific nature. Therefore, having found this specific matrix of the cofactors, we're going to find the transpose over this, which is going to give us the classical adjoint given in that particular case. So I'm going to do away with this since we have already used this particular section. So for us to find the transpose of this, or let me call this one perhaps this is the matrix of cofactors over A, and we are given this one as J elements given in that specific order. So therefore we're going to find the transpose of this matrix by converting the column into a row in that particular case, therefore which is going to give us this is negative 7, 6, 3. So our first column is going to make our first row, and we're going to arrange them in that specific order, whereby we're going to have 2, negative 2, and then 2, and then the last one we're going to have 3, negative 2, 1, given in that specific order. So this is going to be the transpose of the transpose of the matrix of the cofactors. And from our first, of course, definition, we had said that for us to find the matrix or the determinant of a specific matrix, we're going to take that specific element of the matrix according to the Laplace's, of course, expansion theorem. We're going to take these specific matrices, whereby we're going to have the determinant of this matrix given in terms of 1, which is the first element of the matrix, times the first element of this specific matrix of the cofactors, which are going to be given in terms of negative 7, 2, 3, which are this one. So therefore we are going to multiply each element in this with this one. This is a matrix of the cofactor. So the respective, not this one, this is a transpose. So this matrix of the cofactors, the respective multiplication of the respective elements are going to give us a specific product, and this, the sum of this product is going to give us the inverse, of course, the determinant of that particular matrix. So 1 times negative 7, the sum of it, so plus 0 into 2 plus 3 into 3 given as such. So this is going to give us negative 7 plus 0 plus 9, and this is going to give us, of course, a value of 2. So basically our determinant has been obtained from the multiplication of each element of the matrix of the cofactors with the respective element of the matrix, and therefore that's going to give us the first part of that is specific inverse, whereby we're going to obtain 1 over 2, and the classical adjoint, which is going to be the transpose of this matrix of cofactors, is going to be given in terms of negative 7, 2, 3, 6, negative 2, negative 2, 3, 2, 1. So multiplication between this classical adjoint and the inverse, or the 1 over the adjacent of this one, is going to give us, of course, the inverse of this specific matrix. So that's going to give us the value of, just do away with this. So this is going to give us the value of negative 3.5, and then we're going to obtain this 1.5 for the first column, and 3, negative 1, and negative 1 for the second column, and then we're going to have negative 1.5, 1, and 0.5 in that specific respect. So I've taken this lengthy approach so that we can be able to see the relationship which exists between the inverse, the determinant, and the classical adjoint. And this is one of the strategies that we're going to use to find either of these specific elements or part of this inverse which I've mentioned. So from this, given the classical adjoint and inverse, we can find the determinant, or given the inverse and the determinant, we can find the classical adjoint given in that specific respect, since each of them are a subject of another. So that is it for now, guys. Kindly check our description boxes for various links of other videos which are related to this, and of course subscribe to our channel so that you can be getting more updates on various uploads that we do on various subjects in mathematics, physics, and chemistry, and also in biology. So that is it for now, guys. Bye, God bless you. Catch us in our next video.